In the actual setup to measure and characterize a laser diode, the laser diode is placed within this. It's an ILX mounting system, which consists of two thermoelectric coolers, a temperature sensor, and the actual mount for the diode itself. In this case, the mount for the diode, it's a C-mount diode, mounts flat onto it, and the beam comes out of this aperture right here. The beam itself is split up two ways. The vast majority of the beam goes through this beam splitter and into a power meter where we can read the power of the actual laser diode, and a very small portion of it is deflected off the beam splitter and into this fiber, which goes to an OSA. The OSA then allows us to determine the exact wavelength of the laser as well as the actual shape of the curve. The laser diode itself, as you might have determined by now, does not actually output on a single wavelength, but rather consists of a spread out curve over a number of wavelengths. This is how we characterize the laser diode. If I zoom out a little bit, you'll be able to see the actual temperature controller as well. This temperature controller allows us to control the temperature of the mount. So if I set it, for example, for 20 degrees C, the thermoelectric cooler, this device, the temperature controller, now regulates the current through the thermoelectric cooler based on feedback. This particular temperature controller uses a PID control loop to ensure it's an extremely accurate temperature as well. You can see that the temperature is now a little bit below where it should be, and now it'll bring it back up. It only takes a few seconds before it stabilizes the temperature at the exact value that you selected. In our case, 20 degrees C. But we would characterize this diode at a wide variety of temperatures. Now, an interesting thing occurs with all laser diodes in that the wavelength shifts as the temperature changes. So as we warm up the actual laser diode itself, the temperature tends to shift towards longer wavelengths. The actual OSA output you see right now from that laser diode is operating at, right now, 10.3 degrees C. I'm going to increase the temperature to 20 degrees C to show you the effect on wavelength. Now note at the bottom that this is 804.4 nanometers. I've set the temperature controller for a final temperature of about 20 degrees C, and you can see how quickly the output shifts. As a matter of fact, it's no longer on the screen of the OSA. In order to actually see it, I'm going to change the center wavelength to bring it into view. When I change the center wavelength to 807 nanometers, you can now see the actual output curve of the laser diode. So this is at 20 degrees C now. And notice the massive shift that we've seen in output. That at 807, we've moved about a little over 2.5 nanometers towards longer wavelengths, and we're still shifting. If I take it up to about 30 degrees C, you'll find that it shifts somewhere around 810 nanometers. That's a 6 nanometer shift. A very, very large difference. So the output wavelength of these laser diodes is very, very much dependent on the temperature of the diode. The other characteristic of a laser diode is that the output power drops as temperature rises. In this particular case, you're looking at the output power, or rather a fraction therein, at 20.2 degrees Celsius. I'm going to increase the temperature now to 30 to show you the effect on output of the laser. The temperature controller is now set for 30 degrees C, and it's currently at about 25 degrees C and warming. And as the diode warms up, you can see the output power falling. This is another characteristic of laser diodes. In reality, the threshold of oscillation, that is the minimum current to make this laser diode work, is also increasing. At this point, the temperature controller is reading 30 degrees C. So you can note the difference and the decrease that we get in output power of the laser diode as we warmed it up from only 10 degrees C, from about 20 degrees C for its starting value to 30 degrees. It's quite a dramatic drop.